Welcome to EDU World Space.
This is chapter 21, problem number 16. So we have 4-point charges that are placed at the corners of a square. So you can see that, let's call this Q1, the first charge is negative. Then here comes the second charge, is the positive of the first one, positive and negative. So instead of dealing with numbers, first of all, let me set up the problem in a way that initially we don't have to deal with the numerical values, okay? Let's assume that Q1 equals negative Q, right? And Q2 equals Q, and Q3 equals positive Q again, right? And then Q4 equals negative Q. And let's call the length of each side of the square to be A. And we're asked the net force on each charge and the direction of this force. So F net for each charge and the direction of this net of F net, right? So this is actually a very long problem. I'm gonna solve it for one charge. I'm gonna walk you through how you can calculate the F net. And then I'm going to reach a general conclusion so that you can build up on that. Now, so let's start with calculating the net force acting on the first charge that I labeled as Q1, okay? So Q1 is going to experience an attraction as far as Q2 is concerned, right? Because Q2 is a positive charge. So the direction of the force that F2 2 exerts on 1, let's call it F21, right? This F21, let's write it in a vector form. You're going to see that it's going to be easier if you do so. Equals to the magnitude of this force, KQ squared, right? We're finding the magnitude over the distance between the two is A squared times the unit vector. Unit vector, since this force is pointing Q2, while conventionally, again, any force pointing in the positive x direction is defined by the unit vector is I hat, correct? So F21 vector can be written as KQ2 over A squared I hat, because F21 is in the positive x direction. Now let's, using the same logic, let's try and figure out the direction or the vectoral form of F3, 1 now. F3, 1, which means we're calculating the force exerted by the third charge on the first one, on the first charge, right? So let's try to determine the direction of this force. Since Q3 is positive and Q1 is negative, there's an attraction going on between the two, right? So then it's the Q1 is going to be attracted towards Q3, therefore the direction of F31 is going to be down. So let's remember, conventionally down means negative y direction. So we're going to use negative j hat as far as the unit vector is concerned. And as the magnitude is still kq squared over a squared, right? Because the magnitude of the first charge times magnitude of the second charge divided by the square of the distance between the two. Since the distance between the two is a, let's put the unit vector there as negative j hat. So far, so good. Now we have the fourth charge. Let's assume the force exerted by the fourth charge on the first charge is F41. This F41 it has components in both x and y directions, okay? So let me show the direction of it. It's a negative charge and Q1 is a negative charge. There is a repulsion going on between the two, which means Q1 is going to experience a force that is away from this Q4. So this is the direction of F41. Now, I drew it at an arbitrary angle. From geometry, you can figure out what that angle is. First of all, the distance between the two happens to be the hypotenuse, right, of a triangle that has the length of A. So from here, A squared plus A squared, square root of that, A square root of 2 is the distance between Q1 and Q4. Second, if we have a right triangle like this, whose lengths are actually equal to each other, then the angle here has to be 45 degrees, right? Which means the angle here is also 45 degrees. As you can see, F41 is applied with the angle. Let me draw it clearly, right? This is F41. We said that this angle is 45 degrees, right? So let's put it here, 45 degrees. Now let's try and decompose. Let's find the y component. F4y is F4y times sine of 45. Then the x component, F41x, then equals to F41 cosine 45, right? Now, what is F41 is the magnitude, which happens to be kq squared over, this time, let's look at the distance between these two charges. It's a times square root of 2. It's not a anymore. So a square root of 2, and we're going to square this, right? Distance square. This is the magnitude of F41. Now, if we write the vector form of 41, then that would be F41 times cosine 45, right? Because this is the x component, times, remember, F41 cosine 45 is in the negative x direction, so we're going to put a negative I hat here, plus F41 sine 45. It's in the positive y direction, the y component of F41, so therefore we're going to put a positive j hat there. So let's plug in for F41, kq squared over 2a squared, right? This equals to a squared times 2. So, and then cosine 45. What is cosine 45? Is 1 over square root of 2, right? So let's put that in there too. 1 over square root of 2, negative I hat, plus kq squared over 2a squared, and 41 is the same. Again, sine 45 is also, sine 45 equals cosine 45, that equals 1 square root of 2 j hat. Now let's write it a little nicer. Kq squared over 2 square root of 2a squared, negative I hat, plus kq squared over 2 square root of 2a squared j hat. All right, this is F41. This corresponds to the force that the fourth charge is exerting on the first one, the diagonal one. All right. Now, there are three forces, right? F21, F31, F41 that are acting on Q1. Then in order to find the net force acting on Q1, we have to add them all up. Add this guy to this guy to this guy. Let's do it on the new page. So F net, let's call it, for the first charge, okay? In the vector form, equals to F, well, which one we started with? F21. F21 plus F31 plus F41. Now remember, F21 was kq squared over a squared I hat. Kq squared over a squared I hat plus F31, pardon me, F31 is kq squared over r squared negative j hat. Kq squared over a squared negative j hat. And now we have F41. F41 being kq squared over 2 square root of 2a squared negative I hat. Kq squared over 2 square root of 2a squared negative I hat. For the y component, we have pretty much the same. Kq squared over 2 square root of 2a squared positive j hat. Correct? Now, let's group the x components and y components all together. So kq squared over a squared minus, because there's a minus here, kq squared over 2 square root of 2a squared I hat plus kq squared over 2 square root of 2a squared minus kq squared over a squared j hat, right? Now, this term is going to give us the x component of f net, right? So this is x component of f net 1, and this is the y component of f net 1. Let's try to calculate them individually before we go any further. So let's drop, so let's do this. F net 1x, the x component of f net, equals to, if we take this term, right? So in both terms, in the x component, we have kq squared. So I'm going to try and rearrange this term. Kq squared over a squared minus kq squared over 2 square root of 2a squared, right? All right. Now we're going to equate the denominator so that we can do work with it, right? 2 square root of 2 kq squared over 2 square root of 2 a squared. All right, minus kq squared over 2 square root of 2 a squared. From here, we have 2 square root of 2 minus 1 kq squared over 2 square root of 2 a squared. Now it's time to calculate, right? So 2 square root of 2 minus 1, k is 8.99 times 10 to the power 9. Q is given to us, remember in the problem, as 4.15 millicoulombs, so let's convert that to coulombs squared, divided by 2 square root of 2, a, the distance, the length of the side of the square is 0.1 meters, so we're going to square this. From here, we're going to find the x component of the net force acting on the first charge to be 1 times 10 to the power 7 newtons. So doing pretty much the same, f net 1 for the y component. This time we have kq squared minus kq squared 2 square root of 2 over 2 square root of 2a squared, right? So kq squared over 2 square root of 2a squared. 1 minus 2 square root of 2 this time. Let's calculate what it is. 8.99 times 10 to the power of 9 times 4.15 times 10 to the power of negative 3 square over 2 square root of 2.1 meters square times 1 minus 2 square root of 2. So the net force acting on the first charge, the y component of it, is the negative of the x component from here. All right. Well, we're almost there. Now, then, if we found the x and y components, then what is f net acting on 1 magnitudinally is square f net 1x squared plus f net 1y squared, right? So it's going to be equal to 1 times 10 to the power of 7 squared plus negative 1 times 10 to the power of 7 squared. All in all, it's going to be equal, the net force acting on the first charge is going to be equal to 1.42 times 10 to the power of 7 newtons. And how are we going to calculate the direction? Always tangent function. Tangent theta equals to f net 1y divided by f net 1x, as you know. So f net y is negative 1 times 10 to the power of 7. F net x is 1 times 10 to the power of 7. So from here we have negative 1 as the ratio. So the inverse of tangent of negative 1 equals our theta. Theta then is going to be equal to negative 45. So let's remember what this negative 45 means. This is Q1, Q2, Q3, Q4. Negative 41 means that we have the angle that is actually pointing the center. If this is the center of the square, right? Negative 45 means this is 45. Negative, you remember the position is always from the positive x. So then actually this net force is towards the center of the square. So basically, by doing the same process for the second charge, you can show that the magnitude of net force acting on Q2 is still 1.42 times 10 to the power 7. This is true for all of them. So for all charges, F net actually equals to 1.42 times 10 to the power 7 newtons. And the direction is always, for each charge, is towards the center of the square.